This is part of the preliminary lectures. In this part, we shall look at the idea of the concept of a limit of a function at a more advanced approach. The reason why we are taking this advanced approach is not to make your life more difficult, but simply because this advanced approach to the limit of a function is going to be used throughout your second, third, and fourth year at university. Limit of a function. In high school, you already met the idea of the limit of a function. So let's consider the doubling function, and let's consider let's consider the point of approach x naught, which is equal to 3. And using these two data, you know from high school that the limit at the point of approach 3 of the doubling function was equal to 6. And what this meant was that in high school you were taught that as x approaches 3 closely, the corresponding f of x values will start to approach 6 closely. Okay? So notice that, so this is what was going on. So this is your point of approach 3. And then this is your corresponding y value. And what you then did was that you could approach 3 in a straight line. There's only two ways to approach 3 at a given point. You can either approach it from the left or the right. So that's why you drew a table, and then you approached, when you approach 3 from the left, so this is 3 from the left, 3 minus, okay? So you started taking values like 2.9, then 2.99, 2.999, and it began to become much, as you took more 9s, they became way closer to 3. And then you calculated the actual value of f of x. So remember, f of x is a doubling function. So you double that up to 5.4, and I don't know what this doubles up, but you knew that the values were getting closer and closer to 6. Okay? So this is approaching, and then what you then said was that when you drew this table, that the limit when you approach 3 from the left of your doubling function was equal to 6. Okay? You then approached it also from the other side. So remember that in a straight line, there's only two ways to approach 3. And you approach 3 from the right, from here. So in this case, you took 3 to be 3.1. Okay. Then you did it 3.01. Then 3.001. Then 3.00001. And if you double them up, you get 6.2, 6.02, 6.002, and 6.00002. Okay? So in this case, you then set the limit when you approach 3 from the right of your doubling function turned out to be 6. Okay? And when the left and the right hand side limit was equal, you then made the conclusion that no matter which direction I approach 3, there's only 2 of them, the limit at 3 of the doubling function was equal to 6. That's high school maths. So here we have this kinematical idea that as your x marches close to 3, your corresponding y images march close to 6. Okay? And so this is 3. And then this is 6. So remember, you calculated that, so you get it 6. And as your x is marched close to 3, and either from the left or the right, the corresponding the corresponding y's began to get as close to 6. Okay. Now at university, we are going to strengthen this idea of x getting close to 3. So remember, in high school it was as x gets close to 3, x gets close to 3, then f of x will start to get close to 6, okay? Then f of x gets close to 6. Now, in university, what we're going to do is that we're going to strengthen this idea and give you the true picture. It's not just x getting close to 3 and f of x or your y values getting close to 6. Here we are talking about the idea that as x gets close to 3, f of x, the corresponding y images, f of x not only gets close to, but it stays close to 6. So it is not only the idea of getting close to, but it's actually the idea of staying close to. And that is what we mean by the limit at 3 of the doubling function is equal to 6. Let me explain what that means, okay? So let's explain what it means that the y values not only get close to 6, but stay close to 6, okay? So this idea is captured by what we call the formal definition of a limit. In the formal definition of a limit, what you are saying here is, I will first of all write it, and when you see it, you will first of all say what's going on, okay? But then I will put it in a concrete setting, okay? So to get back to our example, it means that it means this, okay? It means that for every challenge, okay? So this epsilon is like the challenge of okay, for every challenge. So you must think of this epsilon as some like positive number that is thrown at you, okay? So it's like saying I want all my y's to be within epsilon close of 6, okay? This will come to see later, okay? So epsilon is known, so that is why we say epsilon is prescribed. So for every epsilon, there is a delta, okay? There exists a delta, okay? Now what does that mean? The delta is the deviation bound, such that if my x's are within delta of 3, this will force the corresponding f of x's, which remember f of x is doubling function, to be within epsilon of 6. This is 6 is the limit, yeah, without exception, okay? So the idea here is as follows, okay? So what we have is here is our 6, okay? So 6 is claiming to be the limit L, okay? So normally we use capital L for limit. Now if 6 is claiming to be the limit of your doubling function at 3, then in order to fulfill this title of being the limit of the doubling function, it means that for every challenge about 6, so let's say I throw down the challenge, I want like so 6 plus epsilon, so within epsilon of 6 either left or right. So remember that epsilon can be very tiny. So for example, I can easily make epsilon be 0.001, okay? So think of my epsilon. So I'm throwing down the challenge. I want the y's to be within 0.001 of 6. Now that is very, very fine, okay? Very, very close. So for this challenge, remember our point of approach is 3, okay? So 3 is here. So here's the 0, 0. So remember 0, 0, okay? So for now what happens here is that, so for this point, what I must say here is that for this epsilon challenge of 0.001, you must rise to this challenge and give me a delta around 3. So your job is to give me this delta. 3 minus, so I must get, so for all my x's whose distance is within 3, within delta of 3, you see, if my x's are within delta of 3, without exception, so for all these x's that are within delta of 3, without exception, if I calculate f of x on them, if I double them up, yeah, so if I double any x without exception, those doubled up x's must stay within 0.001. So in our example, it was 0.001 of 6 without exception. So this is what we call staying close to, you see. So no matter what the epsilon challenge is, so even if I make my epsilon tiny, like 0.000000001, so for this challenge I must find a new delta such that if my delta is tiny, of deltas such within distance delta of 3, such that for all those x's without exception, those x's which are within delta of the new delta of the 3 will definitely be within 0.000000001 of 6. So this is the idea of staying close to, you see. So it basically is the idea of 6, you rise to the challenge of whatever space that 6 needs. If 6 needs a large space, then you rise to the challenge. If 6 needs a close proximity to it, then you rise to the challenge and give x's that stay within that close proximity of 6. Okay, so so let's actually do a concrete example. Okay, so let's prove that the limit at 3 of the doubling function is equal to 6. Okay, now to prove that, to say this, okay, is equivalent to saying for every challenge about 6, okay, so for every challenge about 6, I can rise, you see. So this means, okay, this upside down A means for every challenge epsilon about 6, okay. This backwards E means there exists, and this is your job. There exists a delta, okay, such that if my x's are within distance delta, so your job is to give that delta, then my corresponding y's, which are 2x, will be within distance, okay, this is, remember, the distance between 2x and your limit 6, it will therefore be within that prescribed epsilon. Okay, so pictorially, this is what it means. 6, no matter what epsilon is thrown, I have to rise to the challenge and give a delta of x's about 3, such that if I take any x here, all of them without exception are going to be within epsilon of 6. Okay, so this is the idea of, so this is what is called, so to say this is the same as saying that. Okay, so this is for the first time you're seeing it, so let's repeat it again. To say that the limit at 3 of the doubling function is 6, it means that for every epsilon challenge, so think of epsilon as a positive number that is known, yeah, that's known. Okay, there exists a delta such that if my x's are within delta of 3, it will force my images, which is my 2x's, my y's, to be within distance epsilon of 6. Okay? So to say this is the same as saying that. Okay? So how do we go about this? Okay? So let's show you how you do that. Okay? So in order for you to do that, what you do is that it's very easy. I will show you. If you do these 4 steps correctly, then you'll end up with giving me the correct delta. Okay? So the first thing is you see the distance between the y's and your proposed limit. You have to first of all write that guy. So this is the second distance in terms of the first distance, which is the distance between your axis and your point of approach 3. So you have to write your distance. So your step 1, in order for you to give me my delta, in order for me to calculate the delta, I have to write the distance, the second distance, which is the distance between my y's, f of x, and my limit, as a multiple of the first distance in the definition, which is the distance between my axis and my point of approach 3. So in other words, I have to write this distance 2x minus 6 as being smaller than or equal to some constant. This is a number x minus 3. Now once I have done it, I can now calculate. You see, once I've done this, then it's downhill. Then I know that my delta is going to be epsilon divided by m. Why? Because you see, if my distance between x minus 3, you see, is delta, which is epsilon over m. So if this is the case, okay, remember I can choose my delta to be whatever as long as it does the job. So if my delta is epsilon over m, in other words, delta is the distance, the first distance between my axis and the point of approach 3, then notice that because 2x minus 6 is smaller than this multiple m times x minus 3, then that is smaller than, so remember this guy is smaller than epsilon over m, yeah, because the distance between x and 3 is smaller than delta. And who is delta? Delta is epsilon over m. So I cancel this out and then I end up with epsilon. Then this will then guarantee that my y's is within distance epsilon of my limit 6. Okay? So this is my step 2. Right. So what we're now going to do now here is that that's the overall strategy that you use for all questions. So let's actually let's do it then. Okay. So let's do it. Okay. So let's say you get a question. Prove that the limit at 3 of your doubling function is equal to 6. Yeah. Then what it means is that to say this is the same as saying for every epsilon, okay, every challenge, there exists a delta such that if my x's are delta close to 3, this will force my 2x's to be epsilon within epsilon of my distance epsilon within the limit 6. Then this guy 6 can then say he's the limit. So that's the first thing. Write it out in the formal definition of a limit. So let's call this the 0th step. So to prove that the limit of your doubling function at 3 is 6, you first of all write it out in formal definition. Once you've done it, you see, you take the the second distance. So now let's call this one, okay, let's call this step 0. So our step 1 is we then take the distance between the y's and your limit 6, and you then write it as a multiple of your distance between your pre-image x and your point of approach 3. So let's do that. So 2x minus 6, so who's our m? That is equal to, well, the only reason I'm factoring out the 2 is to expose the x minus 3 term. And then in this case, we then end up with absolute value of 2, absolute value of x minus 3. And then this just becomes 2 times absolute value of x minus 3. Okay? So in this case, as you can see, our m was equal to 2. So the distance between 2x minus 6 is double the distance between x minus 3. Okay, it's twice as long. Okay, then what is our step 2? Then our step 2 is, because our m is 2, we just say that delta is equal to epsilon over 2 does the job. Okay, so we just say delta, which is epsilon over 2, does the job, and then you are finished. Okay, so that's all you have to do. So in this case, let's just draw a table. So let's say that our epsilon, and this is our delta, you see? So think of this as a challenge. So I want all my f of x's or my y's to be within, let's say, distance 1 of 6. So in this case, there's 6. So distance 1 of 6 means 7 and 5, okay? So my job is to find x's around 3 such that, without exception, all of these x's are doubled up into 5 and 7. Okay, so let's see that. So according to this formula, I must choose delta to be epsilon over m, so it is 1 over a half. So let's say so it's going to be 3.5 and 2.5. Okay, so let's just see it. So if my x is between 3.5 and 2.5, notice that when I double them up, I get 5 and 7, which means that my two x's are within distance 1 of 6. Do you get it? So this is quite a big epsilon. So let's be a bit more strict. Let's say I want my epsilon to I make my challenge very, very tiny, like 0.001. Now that's mega strict. So I want all my x's to be, the curfew is very tight, to be within 0.001 of 6. Then according to the formula, my method, I must just take 0.001 over 2, okay, which is equal to 0.005. So if my x's are within 0.005 of 3, which means 3.0005, and that makes 2.9995. Okay, so now you see, so if my x's are within 0.005, will this ensure that my two x's are within 0.001 of 6 and of 6? Okay, so let's double it up. If my x is between that, if I double him up, I get 6.001. And if I double this up, I will end up with, okay, I don't have a calculator, but I can assure you that it will be 5.999, which is 0.001 of 6. Okay, so let's show it pictorially. So here's my 6. The challenge was I wanted it firstly within distance 1 of 6. Okay. Then I rose to the challenge by giving you x's within 1/2 of 3. And notice that all these x's inside here, all of them without exception, were trapped within distance 1 of 6. And the same thing happened with even the stricter curfew of 0.001. And this thing, notice it works for any curfew. Even if you have a curfew as unreasonable as 1 times 10 to the minus 100, the delta that will work is just 1 times 10 to the minus 100 all over 2. So no matter what curfew I put around 6, you can always rise to the challenge and provide x's within delta of 3 such that without exception they stay within that closeness to the 6. So this means it stays close to. Okay, so let's do a final example for this thing. Prove that the limit at the point of approach 2 of my squaring function is equal to 4. Okay, how do I prove that? Well, to prove that, what I do here is that I have to, first of all, step 0, let's write it out in formal definition. Okay, for every challenge epsilon, you see, there exists, so this is my job, a delta, that's your job, such that if my, who's my point of approach? 2. If my x is, this is my point of approach, if my x is delta close to 2, then I can guarantee that the corresponding y's, so remember this is my f of x is equal to x squared. So x squared, now who's the guy that's claiming to be the limit? 4. So x squared minus 4, so the distance between x squared and 4 is going to be within epsilon. Okay, so step 0 is to write out the formal definition of the limit. Now when you write out the formal definition of the limit, you actually end up with two distances, this one and this one, right? So step 1, write the distances between the image, which is x squared, and the limit as a multiple of the distance between the pre-image x, between your axis and your, what is it, and your point of approach 2. Okay, so in order to do this, the first thing is that, so because I want to, you see, I want, so for, in order to do this, that's the only reason I will divide x minus 2 into x squared minus 4. And when I do this division, so remember long division, x goes into x squared x times, so I get x squared minus 2x. I do a subtraction, so I then end up with 2x minus 4, and then this thing will go plus 2 to get 2x minus 4, and I end up with 0. So notice that this x squared minus 4, I can write it out as x minus 2 times x plus 2. Okay, that's the only reason. So I factorize it into x minus 2. See, this is what I want. So then I can, remember this is the absolute value of a product, so it's the product of absolute values. So this is equal to x minus 2 times x plus 2. Okay, and so I will write this out as x plus 2 times x minus 2. Okay, so what I have here is that I've then written out the distance between x squared, the image, the first distance, almost as a multiple of the first distance, which is x minus 2. You see, there I've got it. But you see, this guy is not a constant. Can you see that? It's not a constant because the x is involved. So how do we go about this problem? Okay, so what we do here is that we execute a special maneuver to change this into m. So let's call this step 1.5, because in the previous example this strategy of just dividing into the stuff did the job. So step 1, so we need, okay, let's just call it step 2. So the extra step we now have to take is we have to now, so remember that what we are doing is, remember that when you were doing, when you took the limit, so remember when you said what is the limit of x squared when x approaches 2 or 4 in high school. The way you did it in high school was you looked at those x values that were very, very close to 2. So for example, you did 2.01, 2.001, then you squared them up when you got 4.001, 4.00001, and then you then say, okay, and that. But notice that none of you guys in high school studied at x equals minus 2 or x equals minus 100. So what we can say here is that So our step 2 says that you can fix x's to be within a certain distance of the point of approach. Or because you want it close to 2. X's that are far from 2 are not even, we don't even care about those x's, because we're only looking for x's within. How we're looking at is how does the y values behave close to 2, okay? So that is why, without loss of generality, I can always choose my x's to be some distance within my point of approach 2. Remember, who's my point of approach? It is 2, okay? So in this case, I'm going to say that I want my x's to be distance, let's just say 1, okay? You can pick anything. You can make it 5, you can make it a half, it doesn't matter. But I'm just fixing, so this 2 is my point of approach. So I just choose my x's to be within distance 1 of 2, okay? Now what this means is that, x minus 2 is between 1 and minus 1. And I add 2 on both sides, so this means that it's between 1 and 3, okay? And now you see, go back, you see, this is what is causing all this mayhem, is this quantity x plus 2. So what I do here is that then I just consider x plus 2, the troublemaker. X plus 2 is between 5 and 4. And so I can conclude that the biggest numerical value x plus 2 will ever grow to. So choose who's the biggest numerical value between absolute value 5, absolute value 4. It is 5, okay? So that guy is smaller than 5, okay? So step 3. So if so remember, I have to remember that I made my x's to be always to be within distance 1 of 2. So if x is within distance 1 of 2, then I can write x squared minus 4 as a multiple of what? X minus 2. Remember, because this guy, remember, okay, so this guy is equal to x plus 2 times x minus 2. So he's going to be, now this x plus 2 then just becomes, he grows only as most as 5, because I've restricted my x's to be distance 1 of 2 times x minus 2, okay? So now I've done my job, because I've now written my second distance in terms of a constant multiple of it, okay? And so accordingly, my final step should therefore be as follows. I don't know what it is. Let's call it step 3. So step 3 is that I just take my delta and I just say it must be epsilon over this guy, my m, which is 5. Now we are almost there. Okay. Now remember that this 5, it resulted from our assumption that I'm only considering x's that are within distance 1 of 2. So that is why the real answer, or the accurate answer, is the minimum of 1. Remember, that was my fixed distance. I said all my x's, for all my x's which are distance within 2, the maximum will ever grow to 1. So I choose the smaller between 1, because that 1 comes from there, and this guy, epsilon over 5, and then this will solve the question. And this is the hardest it will ever grow to.